everyone, and today I'm just going to give you an overview of what this solar tracker is and what problems did I have and so on, and why did I make it. So first of all, let's hop right into the objective. So the objective is to maximize the power generated from the solar panels, because static solar panels generate much less power than solar trackers, because sun moves, and because of that the solar tracker also moves with the sun and results in a high power. Now for this project I used 2 servo motors, some wires, Arduino Uno, and 4 photoresistors, some structural parts, 4 10 kilo ohms resistors, and mainly the solar panel. Now let's move on to the current design. In the current design I have got 4 LDRs placed just like so, and between them is a separation which helps the Arduino to detect which side is more darker than the other side. Then we have got the main solar panel over here, which is attached to an axis, which is attached to a servo number 1, which is right over here, and the servo number 1 is attached to some structural pieces so that the solar panel could move, and then that whole sub-assembly is attached to the servo number 2. Now just for demonstration purposes, I have attached the solar panel's power so that once it has focused the sun, the motor and the fan propeller will run. Now moving on to the circuit diagram, over here there is nothing that which is hard, but there is the power supply to the LDR with resistors so that they don't burn off, and these signals go to the analog pins of the Arduino. Then from the Arduino the power supply goes to the breadboard, which goes to LDRs and the servo motors, and the signal from Arduino comes from pin number 10 and pin number 9 to the servo motors. Moving on to the process, the first part is the LDR. So they give the signal to the Arduino, which calculates the average of top, bottom, right, and left, and then it compares between top, bottom, bottom, top, right, left, and right, and then it decides how to move the servo and which servo to move, horizontal or vertical, and then at last the servos follow the Arduino's command, and this process loops around. Then this is the Arduino code. I will not go into the details, but what it does is that there are some variables declared over here, like limit high, limit low, limit high, and limit low, and then there are pin numbers of the LDRs, which you saw in the circuit diagram, and then there is the error, so it doesn't keep moving all the time. Now initially I have written horizontal servo to move 150 degrees and vertical to move 90 degrees. Then over here it reads the servo's angle, which is current angle, and then it reads the LDR's input and converts them into the variables. Then we have got all the average, which I discussed in the process, and the differences, so the absolute differences, so that there isn't any negative sign and only positive signs. So there is written that if the differences are less than or equal to error, then the program should do nothing. It should just stay in that place, which it is, or else the main program shall run, which just compares the two average top, average bottom, average bottom, average top, and so on, and commands the servo to add another to its variable and then write it. So after this, I've got some delays so that the servos get some time to move. Let's move on to the next slide, which is the problems. So the first problem was the axle slip. So the connection between this axle and the servo was not complete. So the servo moved, but the axis didn't move. So that was the first problem, which was fixed when I added some rubber bands to increase the grip of that. The second problem was photoresistors wires, which are behind this. Their weight was restricting the movement of the solar panel. So I just switched to more flexible wires and lightweight wires. Next is the coding. So this is a problem because I didn't get how to code so that the servo will move with the signal of the LDRs. Now, so this design is slightly asymmetrical because this side's weight is more compared to this side's weight, so the servo 2 problem was there. Now, angle calibration. So if you program it to 90 degrees, then the solar panel should be flat. So that you have to give the command to the servo number 1 to be at 90 degrees, and then you attach the solar panel. So that is called angle calibration, and it was major problem. And the sixth was no wire flexibility. So I attached the normal wires that we use, which are stiff, and right now I've just updated them to the flexible wires. Now, as for the future plans, the improvements are that design will be more rigid and symmetric, so that the servo number 2, which is horizontal, doesn't get any problem, and it will be more reliable. The second is improve the accuracy. So right now it is not very accurate, and I will update the code so to make it more accurate. Then I have the third improvement that I will do is that use the solar panel for specific purpose, like charging your mobile battery and things like that. Moving on to the next one, I've just calculated estimate costs. So this is the basic, which contains a single axis, and it is a prototype, and you get the code in there. And then it will cost around, if you build it with your own hands, it will cost around 300 or 400 rupees. Then in this one, you get dual axis, and it is still a prototype, and you get the code, which will, if you just make it by your hand, will cost around rupees 750. If you go into premium, the dual axis, there is dual axis, and it is final, which I discussed in last slide, that the structure will be improved. So that and plus the code, that will cost you around 800 rupees. So the structural parts are much less in the premium than they are in pro, so that is the reason why the cost is around the same. And lastly, thanks.